Hi, everybody. Carrie here with the National Snow School Program and Winter Wildlands Alliance. And I'm really excited to have with me Hans Peter Marshall, HP, Associate Professor of Geosciences at Boise State University, snow scientist, and also happens to be our Winter Wildlands Alliance Snow School Ambassador. Had a lot of collaboration and partnership through the years, which I'm really appreciative of. And again, thanks so much for joining us, HP. And I wonder if you'd be willing to just tell us a little bit about your areas of expertise and interest these days as a snow scientist.
Yeah, absolutely. Thanks for having me on. I'm excited about this conversation. Um, yes, I'm a snow scientist. I'm here at Boise State. I have a background in physics and engineering and kind of started my journey in snow science more on the glaciology side of things. So worked on the Olympic Peninsula, on Blue Glacier, and spent some time in Antarctica and Greenland. And since moving to Idaho, have kind of shifted a lot more to seasonal snow in the last several decades. And so a lot of our work is funded from the perspective of water resources. So trying to improve tools to measure snowpack properties. We do that from ground-based observations. We go out on skis and snowmobiles and take observations in the mountains here, and then we put instruments on drones and helicopters and fixed wing aircraft. And now finally we're getting to the point where we're transitioning some of this to data that we collect from spaceborne platforms, so satellites. And the goal there is just that as you get to these platforms that are higher off the ground, you get to cover a much bigger area, and so it becomes more relevant from a water resources perspective. But when we're really close to the ground, we can understand the signal a lot better. We
Mm.
can dig a snow pit right in the place that we're measuring and kind of really develop the what we call the retrieval algorithms, where we take those measurements and turn them into quantities that people care about, like snow water equivalent or snow depth or snow melt. Um, so
Yeah.
that's the bulk of a lot of the work that we do. We also do some work around avalanche related research, avalanche monitoring and detection and modeling. And then we do a fair bit of work for the Army Corps of Engineers, the Cold Regions Research and Engineering Lab. And that work is more focused around military mobility in cold regions and snow covered areas. And that's connected us with a lot of wildlife folks that are also interested in sort of over snow mobility of animals.
We have been partnering for a lot of years on a variety of initiatives here. And this project that we piloted with you this year with the NISAR satellite, um, it really felt like this was a moment that was a long time in coming. We had a NASA satellite in orbit, specifically the NISAR satellite, with snow sensing instrumentation on it that you're interested in tracking. And then from the snow school perspective, we had our National Snow School program, students and educators on the ground at our national flagship site in the Boise National Forest at Bogus Basin, uh, specifically collecting some snowpack data with the intention that they're going to share it with you and your team to compare to the snowpack data that you're collecting from the satellite to help you and your colleagues figure out a little bit more about how much water is actually out there in the form of snow. So that felt like a really big moment. We've been working on this for a long time, and I wonder if, before we launch into the specifics of it, you could back up a little bit and maybe just explain a little bit about how we got here, like this grander idea of we need a satellite in space to help measure the water content of snow.
Yeah, I mean, I think some of the compelling numbers, especially in the western US, seasonal snowpack is roughly 70% of our water supply.
Mhm.
Globally, 1/6 of the global population, so getting close to several billion people depend on seasonal snow for their water usage. And so it's obviously an important resource. You can kind of think of it as our largest natural reservoir that turns over every season that we need to monitor. One of the challenges is that we've never had the right sensor up in space to actually measure how much water we store. What we can do right now operationally really well as a community is we can say where there is snow and where there isn't. So we would call that snow presence or snow covered area. There's a lot of people that have done a lot of really good work in that area and even resolved it to like a fractional snow covered area. So you get a pretty good sense of what percent of the landscape at really high resolution. I'm on the order of, 50-meter kind of pixel size where there is and isn't snow, but it doesn't tell us how much snow is actually there. And so rather than using, the snow covered area estimates come from optical imagery. So similar to the way that our eyes would see the snowpack, we can see white as very different from, say, brown dirt, for example. But we really, in order to probe the snowpack and get a sense of how deep it is, how much water it represents, we need a sensor that actually goes into the snow. And that's a more challenging thing for us to interpret, and that's why we're using radar. So radar is also an electromagnetic technique, and the wavelength, instead of being sort of on the scale of like a micron, we're talking about wavelengths on the scale of like 20 centimeters. Um, so, think about a wavelength that's on the order of about a foot. It's actually can penetrate right through the snowpack. And this kind of radar basically moves right through the snow, bounces off the ground underneath the snow, and then comes back. And what we do is we use the amount of time that it takes for that signal to go from the sensor through the snowpack to the ground and back again. And that, what we call time of flight, is related to how much water is actually there because the signal slows down as it goes through the snow, and how much it slows down depends on the density. We need to be able to use remote sensing to map our snow water resources, largely because snow just varies tremendously over the landscape. And for anyone that's spent a significant amount of time in the mountains, you can travel from one side of a ridge to another and go from very little snow to giant drifts or cornices. And even off outside of the ridge areas, typically when we make a measurement in the snowpack, it's representative of about a football field around that point. So you can kind of think of a lot of people are pretty familiar with the SNOTEL network. If we wanted to install enough SNOTEL sites where we could actually estimate what was going on in between them, we would need a SNOTEL site almost every football field across the
Mm.
entire West. And that's orders and orders of magnitude more than we could really ever do. Um, those SNOTEL sites are super critical, and they measure exactly how much snow water equivalent we have on the ground. So they are our best piece of information other than when we go out and actually dig a hole in the snow and sample it. We really need this spatial context. And so even though the remote sensing is a little bit more challenging to interpret, it's the only tool that gives us measurements over the entire globe or over the whole Western US. So that's sort of the need for these satellite observations. We've been trying to get a satellite in space to measure snow since I was a graduate student in the early 2000s. So
Oh.
2002, 2003 was the first really big community-wide NASA campaign that really was targeting trying to figure out what sensors could we put in space to actually make this measurement.
Yeah. And a lot of what you just described there are things that we've got Snow School students doing at Snow School during their field trip. So that thing about the geospatial variability of the mountain snowpack, we have groups of fifth graders fan out over a little drainage on the north and the south side, and kids are digging snow pits. They're measuring snowpack depth. We're looking at the crystal structures. They're talking about like the different depths that they're observing in these different locations through Snow School. And then some of the other like hands-on things that we have going on. Of course, the water content is a big part of it. Sometimes with Snow School, it's through these, density cutters and extracting samples of snow and measuring the water content. Other times it's through, where's my very simple snow water equivalent experiment canister that we do with younger students, where you simply scoop up 6 inches of snow, and then everybody makes a hypothesis about how much water is going to be in there when you microwave it. It helps. give a demonstration for that concept that you're talking about of like how much water is sitting on the ground in the form of snow out here. But what we did with this, the NISAR project this year is different from anything that we've done before. We had the interval board, and I've got it here behind me. This was up at Bogus Basin at our snow school site there in the Boise National Forest, and we used these snowmetrics tubes. And every day, the snow school educators and students visited the interval board to see how much snow had accumulated,
Mhm.
um, and to keep track of this over time. If you had on a given day snowfall in the morning when the students arrived, and the educator and the students came up with the snow tube, used a simple spatula, flipped over the sample here, and they've got their depth of snow here. Say it's about 5 centimeters of snow in this tube, and then weighed it, um, and recorded basically the weight of the weight of the snow of this sample of snow. And on one particular day when they collected 5 centimeters of snow depth based on the volume of that tube. If that was all water, that'd be like 120 grams or so that it would weigh. Um, but when it only weighed 25 grams, they could have the discussion that, oh, this was about 21% of water in the sample. Thus, out of your 5 centimeters of snow depth, you've got about 1 centimeter of water. And
Yep.
so having that discussion, there's actually not that much water uh, in our snow, which is important why we understand how much snow is out there. We keep track of it. But we recorded this every day. And I know that the NISAR project does is interested in like these 12-day intervals,
Right.
and specifically what the change in snow accumulation is over time. And so, like for example, there was a 12-day period in February where we collected these every day, and it amounted to a couple centimeters of snow water equivalent.
Yep.
Um, what is your team who's looking at this NISAR data, knowing that location, hoping to be able to extrapolate regarding the water content in this area and in the mountains?
Yeah, so I the the nice thing about NISAR is that it really is kind of more directly related to the change in SWE than it is to the change in depth. And like you said, the density can really vary a lot. If you're in Utah in like the lightest, driest powder that you can imagine, you're talking about like 3% water. And if you're out in the Sierra Nevada at a relatively low elevation and it's a really super warm snowfall event, I mean, that could be 25, 30% water. So we can really vary by like a factor of 10 in terms of that density. And that's why that observation is so important. And the reason it's also so important on that interval board is because we really want to know how much snow fell over that 12-day interval. And sometimes, you could have conditions where a big ice layer formed maybe right on the start of that 12-day interval. And if you went back 12 days later, you'd be able to find that ice layer and know how much change there was. But often it's hard to identify where that surface actually was 12 days ago. And so what that interval board does is it's a marker of where the surface actually was.
Mm,
And the reason that's a lot better than, say, going out and digging a full pit and measuring the total snow water equivalent and then doing it again 12 days later is we can't do it in exactly the same spot. We have to move to a different spot because you've disturbed that place.
mm,
And like we were talking about sort of the just the variability that exists in the snow cover, if we dig in a different spot and we measure a different SWE and we're trying to take the difference between these two snow pits 12 days apart in slightly different locations, we don't really know how much that difference is just spatial difference and how much is like a difference in the accumulation over that 12-day period. So those are really unique measurements. We're pretty efficient at measuring depth.
mm,
We often use either drone based or helicopter based or fixed wing based scanning LiDAR observations to measure snow depth. So that's become a very practical and mature remote sensing approach. But again, it only still only gives you depth, and we really need that density in order to convert it to an amount of water. But also, that density comes into the way we interpret that time of flight measurement from that radar from the satellite and turn that into a change in snow water equivalent. So the data that you've collected with SnowSchool is super valuable. We don't have that many places where these interval board measurements are made. There are a fair number of ski areas and avalanche forecasting operations, and we're trying to build a common database around that. But it's also a really straightforward measurement that can be made that I think kids can get a lot out of in a sort of real hands-on way. And it doesn't take as long as a snow pit either, right?
Yeah, absolutely. Especially, well, the snow pits that we had this year, perhaps.
Yeah.
Those are quicker to make. But on a typical year, fingers crossed, we get more normal years here. Yeah, snow pit takes a lot of energy, and it's a great point. Snow School is uniquely positioned to do a lot of this. I know a lot of our educators and Snow School site leaders across the United States are interested in participating in this. So as we move out of the first year pilot of this idea, and we're now sharing this with other snow school sites, what do you think is like the impact of other snow school sites across the country, across the West, participating in this project in the coming winter?
Oh, I think the impact is huge. I think with a lot of these remote sensing tools, we can collect a ton of data really, really fast, right? We can cover these massive areas and get super high resolution information. But in the end, when we're trying to develop a tool like this, the most useful data, and really the only data we spend a lot of time working on, is the data that comes from the places where we have ground truth observations. So by a snow school starting to make these observations, that will become a target for where a lot of the NASA and university and government lab scientists that are working on this NISAR effort will start really focusing. And every one of these NISAR images has to be pinned down to a place where we know what the snow water equivalent change was. And
Right.
so if you're a location that's measuring that, and we can use that to pin this map of relative change down, then we can use that map with the satellite data to predict what the snow water equivalent change was over a really big area around that point. And without having that point, we sort of don't have anything to tie it to. And so these ground observations are super critical, and the snow community has come to consensus that there won't ever be a single model or a single remote sensing tool that's just going to give us all the information we need about the snowpack. We're always going to have to combine a modeling effort with a remote sensing effort with ground observations like what are made at Snow School. But the big exciting thing about NISAR is that NISAR's covering every square inch of the planet every 12 days. So it doesn't matter where you are. No matter where you exist, there is going to be an overpass at least once every 12 days. And actually, it's more often than that. If you consider the satellite does an ascending pass where it's moving from south to north, and then a descending pass where it's moving from north to south. And so most places have an overpass every week. Um, and so that just opens this opportunity to get involved with a NASA remote sensing project for every single snow school that's out there. One of the challenges with this particular technique is it gets really tricky when the snowpack gets wet.
Yeah.
So with a warming climate, if we have a winter like we did this year, I think it'll provide really good information at the higher elevations, but at the lower elevations where we're getting midwinter rain, midwinter melt, as long as there's liquid water in the snowpack, that's going to make this technique challenging to apply. If
Mhm.
that water drains and then refreezes and we get a big, you know, cold front that moves through, then the technique can start working again. But that's sort of one of the also important observations for these interval boards is not just the snow water equivalent on the board, but if there was evidence of melt,
Right.
just because it really affects the measurement a lot. So I guess that's one challenge. Another challenge is just having enough ground data to really develop these algorithms, and I think
Right.
Snow School can play a really big role there. Um, The other challenge I would point to is just science funding in general. Like, we're having a lot of challenges with science funding in terms of what proposed budgets are right now at all of the major agencies. You know, one of the big pieces of information we really need to get this technique to work is really good information from weather models. And right now, the National Center for Atmospheric Research is kind of getting dismantled. And that that group that's based out of Boulder produces the cutting edge weather models that we use to feed our snowpack models, but also that radar signal that goes from the satellite all the way down through the atmosphere, through the snow, and back again, it is affected by the atmosphere. So we actually have to make corrections based on the current weather conditions, the weather conditions on the first satellite overpass, and how that's different on the second overpass 12 days later. And so if we start losing a lot of that weather information, this is going to get a lot more challenging for sure.
Yeah, that's really important perspective to share. And I know that you've been doing a lot of advocating for science funding and snow science funding yourself. And we've been working with our partners over the last couple of years as well to make sure people kind of understand all the different aspects of our lives that this stuff touches. Everything from certainly our water supply and agriculture, but recreation. We put out a story this time last year about the importance of having this snow science data to inform safety, whitewater safety on trips that people take, rafting trips people take on the Salmon River in Idaho and elsewhere. There are so many elements of all this. I mean, snow is so critical to our way of life in the Western United States and beyond.
Yeah, I mean, snow is so important for Idaho in general. I think it's a story we can talk to anyone about. I don't think it crosses the aisle. It shouldn't have any sort of political affiliation in any way. Science doesn't take sides, and Idaho depends on water for farming and ranching and agriculture, and um, it's important for everybody. And so I had some really good conversations with our lawmakers in DC last week, talking about that importance, and they definitely expressed concern for what's going on with the Forest Service right now, and the National Center for Atmospheric Research and science funding in general. And I think it's important for people to reach out to their lawmakers and express that. I don't know if you followed, but in our 2026 fiscal year uh, federal budget, the original proposal by the administration was for 50 to 60% cuts across most of the scientific organizations. And what Congress actually passed in a very bipartisan way was more like 4% cuts. And so those conversations that you have with lots of different kinds of people across the political spectrum, and hopefully folks can be kind of reaching out to their lawmakers, they do have an impact. That is a way we can move the needle on this stuff.
Yeah, here at Winter Wildlands Alliance and SnowSchool, we're definitely going to be leaning into the grassroots effort here to make a difference, to spread the word, to talk to the decision makers, and to contribute to snow science here, to make these measurements in the coming year to help this effort and help your work and advance science that is important to all our lives. So. Thank you so much for being a part of the call here today and for your partnership through the years and all the work that you're doing. And looking forward to our next update on all this when we talk again.
Absolutely, Carrie. Thank you so much. You're training the next generation of snow scientists, and even those that don't go into snow, I think get a really good sense of how important field observations are, and it really connects to science as you've shown in a lot of your work, how important these kind of field observations and experiences really impact learning. And I know that I talk to lots of students that come to Boise State that have had that experience as kids at SnowSchool, and it's made a big impact on them. So thank you for that work.
Thanks for sharing. We're going to keep those memories coming.
Yeah,
And yeah, really appreciate it. Thanks.
thank you.